for inviting me. I'm glad that you pronounced it the English way, CaJAGWR, rather than CaJAGWR. I will be talking about, it's a rather silly title, I'll be talking about standard sirens, gravitational wave standard sirens in general. I'm not sure I will tell you what they actually have to say, but that's what I'm going to be talking about. This is I always like to talk about this to start with. This is a view of lovely Glasgow University, where I'm from, or where I work. And just out of shot about here is where you would have Lord Kelvin's house that he lived on campus. And it was the very first house to have electrical wiring that he wired himself. So, on to my talk outline. So first of all, I'm going to motivate what we're speaking about, cosmology, gravitational wave cosmology, and talk about the current state of knowledge. Obviously, this doesn't come from gravitational wave astronomy because we don't as yet detect them. Then I will talk about the main ideas in gravitational wave cosmology, specifically standard sirens, and some arguments based on statistics of sources that we'll detect. And I cut out space-based approaches because I'd love to talk about it, but I do go on and on and on about these things. And I would like to get to this bit, which is the bit I was invited by Sarah to actually talk about, which is some recent ideas about cosmology regarding tidal signatures of neutron star binaries and using a particular phase of the merger, or the post-merger of neutron star binaries to do some cosmology. And then I'll summarize if I get to the end. Okay, motivation. So this slide is probably wasted on you guys. What I wanted to really say is that this talk and standard sirens are, I'm only going to be talking about compact binary coalescences, so inspirals and mergers of compact sources, black holes, neutron stars. I won't be talking about any other stochastic background, continuous waves, burst sources. And so, yes, just wanted to discuss that to start with. And also, I shouldn't have to say this for everybody, that we are on the verge of a very, very exciting time where we're going to be detecting gravitational waves in the next five years or so. And I should say, again, it's the 2015 epoch. We're getting ready for 01, the first observing run of Glasgow. And although the expected detection rates of binary neutron stars are in the low end, the realistic number is in the middle of these two numbers, and it is below 1. There is an optimistic chance of detecting more than 1. So in 2015, it's very exciting, and if we're willing to wait for 2022, it's incredibly exciting, and we would expect to have more than 1, possibly up to 400. And that's not just for binary neutron stars. This is an older paper people may be aware of, where they're talking about neutron star binaries, neutron star black hole binaries, and black hole binaries, and they have very similar expected rates of these events. But most of the talk here is about binary neutron stars, with a little bit about binary black holes. So, gravitational wave detection alone will be absolutely great. There's no denying that. A lot of people are trying to achieve that right now. What I want to be talking about is what we can do after this. And in order to do some gravitational wave cosmology, we need more than one detection. We need tens, if not hundreds of detections to do something impactful. So what I want to be talking about is this thing highlighted in pink. Precision mapping of the expansion history of the universe, using gravitational wave standard sirens, using these as cosmic distance markers, otherwise known as standard sirens, and hopefully showing that these might provide a powerful probe to the dark energy content of the universe. But more importantly, initially, simply to make independent measurements of some of the more basic cosmological parameters like the Hubble constant to start with. So, skip over, sorry, that's not for me, it's for you. Current state of knowledge. So, the cosmic distance ladder. So this is how we know things, how far things are away from us cosmologically. I'm always surprised by this, because I always think knowing the distance of something is such a fundamental and simple concept that it shouldn't have any difficulties associated with it, but it does. We start off, it has difficulties with it because you can't go up to an object and measure its distance with a ruler or something. So we start off in the solar system, and we're able to do very, very accurate measurements within our solar system using laser ranging, and we can make our baseline measurement of the astronomical unit to about 1 part in 10 to the minus 11 accuracy. But then we step out into our galaxy and we start doing parallax measurements of the distance to stars using this baseline measurement we have of the Earth moving around the Sun. this starts to propagate errors. Our errors increase as we look at further and further stars to try and get their distance. Beyond that, you start doing things like main sequence fitting, where here you have a relationship between the expected luminosity of an object and its particular property, in this case, its temperature or color of a star. And if you can measure its temperature or color, you can infer what its luminosity is. If you know what its intrinsic luminosity is, and then you measure an observed luminosity, you can work out how far away it is. But again, this is a bit of a mess, slightly messier than the previous stages. It's also building on the previous stages to calibrate against. So you're increasing the error as you go further and further out. Then there's other relationships like the pulsation period of things called scepter variable stars, where you can measure that quite accurately, but then you have a relationship between the period and the luminosity, and it's the same idea as done with the main sequence fitting. And then further out, you're looking at the relationship between luminosity of galaxies and their rotation curves, how fast they're spinning, or the dispersion measures of the stars in those galaxies. So what I'm trying to say is, there is a ladder to working out cosmological distances as you get out to these kind of distances. I think I can never do the conversion, but light years are not far from parsecs. So this is about 10 gigaparsecs over here. And just to stress, nearby objects are used to calibrate more distant measurements. And what I want to say is that gravitational wave measurements will be completely both independent of this ladder entirely, and also not reliant on multiple stages in a ladder. There's no ladder for gravitational waves. It's just one continuum. We can measure luminosity distances to these objects without relying on these distances to calibrate this. So a few concepts, a few things I'll be talking about, just to define them at this point. This thing on the right is sometimes known as the Hubble diagram. And it's plotted in various different forms. This form, I'm going to have redshift on the x-axis and luminosity distance on the y-axis. And depending on the cosmology, depending on the cosmological parameters that govern our universe, then you get a relationship between these two quantities: the redshift, the recession velocity of objects, and the luminosity distance we measure. So different cosmological parameters give you different curves, and I can't remember which ones the particular lines are. The redshift here is related to the recession velocity of an object, and the luminosity distance is a reasonably complicated function of this thing, this Hubble parameter, which itself is a function of the cosmological parameters. In this case, classic Hubble constant, followed by the energy density of the matter in the universe, the curvature energy in the universe, the dark energy content in the universe, and some dark energy parameters along here. For advanced LIGO, for initial gravitational wave detections, we will be insensitive to most of these. We will hopefully be able to constrain the Hubble constant. But for third generation and beyond, then and space-based missions, all of these parameters are opened up to us for parameter estimation. Okay. So, standard candle. This is the analogy to standard sirens that I'll be talking about. And it's kind of the clues in the name. These are things that are of constant or well-known consistent amplitude. Consistent amplitude or known luminosity, which, when you measure something that is consistently supposed to have the same luminosity, and you measure it, you observe different luminosities, you can immediately infer how far away something is. And so the standard candle is type 1a supernovae, thought to be white dwarf stars accreting mass from a companion object, pushing it over the Chandrasekhar limit and going supernova. And all stars are supposed to be doing this pretty much the same within a very small error, and the luminosity of the explosion that you get is supposed to be consistent throughout the local universe. So, I put here that I think the luminosity is known to approximately 15%. And what you see here on this axis, the top panel is showing redshift on this axis, so it's a bit like the Hubble diagram, except on this axis, instead of luminosity distance, it's something basically proportional to the log of luminosity distance. And it's the difference between the observed magnitude and the absolute magnitude of these stars. And you can see they have lots and lots of supernova that they've plotted on here, and then they can start fitting curves and constraining cosmological models. And here's their errors on this thing. But, as I said before, there's a calibration required. you don't actually know the absolute intrinsic luminosity of supernovas, you just know that they're all the same, or supposedly roughly the same, and so you have to calibrate against something else. So recent calibration against Cepheid variables, which themselves calibrate against lower rungs of the ladder, give a Hubble constant of this value. That's a 2011 measurement, but it's a 2014 supernova. So some more current, the most up-to-date current knowledge cosmologically is coming from the 2015 Planck results. And here's the famous map that keeps changing every couple of years, getting slightly finer and more accurate, discards cosmic microwave background. And here is the multipole sort of decomposition of this map. And the fit to this data, the very accurate fit, is different to the Hubble parameter fitting. It's a different, different to the Hubble diagram fit. There's a different function that is a function of the cosmological parameters that they use to fit to this data. And this gives us the most accurate knowledge of cosmological parameters that we know to date. It's considered to be consistent with the Lambda-Koldal matter model. Nothing crazy going on with what they're seeing with this result. And he gives a Hubble constant here. And if you just flip, this is 67.8 plus or minus 0.9. If I flip back to this number, 73.8 plus or minus 2.4, there's a little bit of tension between these results that people are trying to resolve at the moment. And I'm sure that people who know far more about this would say this isn't currently an issue, but I'm going to jump on it and say this is an issue that will help us, gravitational waves, we can come in and solve all their problems. But that's probably not quite the case. And so one other thing I need to stress, because this annoys people, both in gravitational wave and EM communities, is anything that we say about what gravitational waves can do in the next 10, 10, 15, 20 years is not fair to compare against what Planck and EM community are doing right now. We really should be comparing against what they're going to be doing in 5, 10, 15, 20 years. So it's unlikely, before the Einstein telescope at least, that we will be competitive with estimates of cosmological parameters. But what we will do, and I keep stressing, is that we're going to be completely independent. So it's a completely independent measure that we can use to calibrate their results. Yeah, that's what I'll help with. We'll calibrate them. Right, on to gravitational wave standard siren. So sorry for the childishness of some of these plots. It's how I think about these things. So standard candles, here we have the Earth. We have the animals roaming the Earth, trees, our moon, and what I like to, this is my representation of an optical detector, a telescope pointing into the sky. And here we have two galaxies with two standard candles in them. They're both supposed to be the same intrinsic luminosity, but we see this one as 4 times brighter than this one. And therefore, by the inverse square law, we can infer that this one is twice as close as that one, and then we can start doing cosmology, and that's the basic idea of these standard candles. So it gives relative distances, but I'll keep stressing, still needs calibration. So here is gravitational wave standard siren. You can see what changed here. A couple of things. This has now become an ear. This is my ear. It's very difficult to get that exact shot. Because gravitational wave detectors are, we could say they're analogous to microphones and listening to the universe rather than seeing it. There's no longer, so now we have two standard sirens to say compact binary coalescences in these two galaxies. This time, however, based on how we define loudness, we'll see this one is twice as loud as that one, which means twice as close. Because we don't have the inverse square law, we have just inverse law because we're measuring amplitude rather than intensity of radiation. And, I keep stressing it, gives absolute distances. There's no calibration against anything. The only thing that comes into these are our well-known constants that go into our waveform calculations. Speed of light, gravitational constant, and so on. So, no calibration required.
Can you explain that at all?
Explain.
That last bit.
So, the point is, when we make a measurement of 2 binary neutron stars and 2 black holes, then one of the parameters that we estimate is literally the luminosity distance. It comes straight down. So there'll be errors associated with our uncertainty in measuring other parameters in that waveform, but it's not something we have to calibrate against something else. So, step back for 2 minutes. So, in 1986, Bernard Schutz proposed this idea that then turned into the idea of standard sirens. He didn't call it standard sirens, that was called standard sirens later on, as something else. And there's Bernard there. The basic idea is if this is a typical compact binary coalescence gravitational waveform of the inspiral, we're just talking about the inspiral here, then we are able to very accurately measure the phase information in this waveform. So just think about the phasing of it. The phasing is a function of time, but it's also of the parameters of the problem. It's a function of this thing known as the chirp mass. And in this case, it's a function of what is known as the redshifted chirp mass, which is this thing here. It's the chirp mass multiplied by 1 plus Z, where Z is the redshift. The chirp mass is the total mass of the system multiplied by the symmetric mass ratio of 3/5. So this is the symmetric mass ratio, where that's one of the component masses, that's the second component mass, and again, that's the total mass of the system. But for the majority of the talk, if I say chirp mass, you can say mass. It doesn't really matter for the basics. What does matter is when I say mass, chirp mass, and redshift chirp mass. That's important. And I'll try and get that right. When we measure one of these sources, we will make a very accurate measurement of chirp mass. Redshift chirp mass. When we measure the amplitude of the source, which we do simultaneously in data analysis, we'll pretend we just do it separately, then you're making this amplitude as a function of the chirp mass, which you just measured incredibly accurately, and the luminosity distance, how far away this thing is. So, by getting this, you then plug it into here and you get this estimate of the luminosity distance. And so this was the idea that Bernard came up with, that we will be able to measure luminosity distances very accurately to these sources. And this is the self-calibrating idea. Right? But one thing I want to stress is, we don't measure any redshift. So if you're trying to put this thing on a Hubble diagram, somewhere on that plane, right now we only get the y-axis, we don't get the x-axis. And that's it, that's the key. So, I want to see how many people are aware of what that picture is. I guess it's just mostly the Europeans. There's only like 3 people. There's Joe that's telling us. Okay. So the point of this is very simple. As I said before, we measure a redshifted chirp mass. So I've established we've measured the luminosity distance. And now let's go back to the chirp mass. We're measuring redshifted chirp mass. We have not measured either of these quantities, M or Z, separately. We only have the one quantity. We cannot disentangle these. If you go to a chirp mass redshift plane and you plot your result, it just defines a curve on here. Right, this is just my sketch of this. So you don't know whether you have a source that is at a low redshift with a high chirp mass, or a source which is at a high redshift with a low chirp mass. You just don't know this from this result. And this is from a sitcom called Father Ted. This is where they're explaining to Father Dougal McGuire that cow is small because it's close to him. And the ones in the field are small because they're in the field far away. Right. So this is known as redshift, the chirp mass redshift genesis. And I will come back to that in a second. Well, no, this is related to this. So one way that you can break that chirp mass redshift degeneracy and obtain a redshift is to start using electromagnetic counterparts. And so we have this idea that gamma ray bursts are associated with binary neutron star mergers, and if we happen to see both of those simultaneously and associate them as the same object, then you can go and look at the gamma ray burst, identify which galaxy it came from, and obtain the redshift after the fact. And then you're able to put this point on the Hubble diagram. And on the left-hand side, this is a plot of one of our papers, one of the LIGO, no, it's not one of the LIGO papers. We did an analysis on GRB 051103, James Clark did this analysis, where there was an idea that the gamma ray burst had gone off in a local galaxy M81. I can't remember the distance, but it's certainly within the initial LIGO distance. So had that gamma ray burst given off a binary, had that gamma ray burst been in that galaxy, we would have seen it in our initial LIGO searches. And this search was done, and it was not seen, and so we could rule out the fact that thing was in that galaxy, but that's an aside. So the idea is that, as I said before, if you associate a gamma ray burst with these things, you can get a redshift. The problem with this is that not all gamma ray bursts are going to be beams, there's going to be a directional issue with these things. Not all of them will be seen by us, so only a small fraction you might imagine would be seen coincident with a gamma ray burst. And therefore, a smaller number of sources you can put on your Hubble plane. This is a block from another piece of work, 2010, where I think it was CaJAGWR and Chris Van den Broek looked at, and others, maybe Chinese, yeah, it's Chinese at one, where they looked at the Einstein telescope in the future and seeing how, and the number of sources you may expect to see both in coincidence with gamma ray bursts, and seeing what you can do with regards to the dark energy parameters specifically. I think the idea is there is assuming when ET comes along, the EM telescopes would have constrained all the other cosmological parameters really well. You can fix those and then ask how well the gravitational waves come along and help us with dark energy equations there. Okay. This is where I had too much time to spare and I made fancy sort of, not animations, but I'll try and go through this. This is very simple. It works for kids, so I'm sure it'll work for you guys. Right. So this is Schutz's method. This is Schutz's basic method, following, if you all remember what I talked about before, where Schutz said that you can measure luminosity distance, but you can't get redshift. However, you will associate a region of sky with a particular source. So before I start, let's do a very simplified version of Hubble's law, or the cosmological relationship between luminosity distance and redshift. So for very local distances, these are just linear relationships, one's proportional to the other, where the constant of proportionality is C over the Hubble constant. I've set up this plot here. This is a Hubble constant on here, and this is a count. I'm going to make a histogram as I go along, and this dashed line is the true value of the Hubble constant, which we don't know before we start the analysis. And lo and behold, very smoothly, we detect our first gravitational wave. This gravitational wave gives us an error box on the sky which contains 4 galaxies. For each of those galaxies, I'm going to assume that was the source of my gravitational wave, and I will use this expression together with my measurement of luminosity distance that I got from my detection, and I will compute a potential Hubble constant for each of these galaxies. So that's what these red numbers are, and I will now histogram those values. So I happen to have 2 values between 20 and 30, and 1 between 40 and 50, and 1 between 60 and 70. And typically, this is the size of the error box that Bernard Schutz in 1986 predicted that we would have 6 degrees by 6 degrees. It's a little bit over ambitious, but not far off what we really will be seeing with advanced light full sensitivity. Then if I continue this, you guys seem to be picking it up quite quickly. So I'll go faster. Here's the second gravitational wave that we have, and I've got 4 more Hubble constants, and I will histogram them, add them to my histogram, and I will go on to the third detection. There we go, only 3 galaxies in here, I've added to the histogram, and then finally, a 4th detection, 3 more galaxies. But in all of these, under the assumption that one of them in each of these panels was the true galaxy, then that true galaxy will start to add coherently in this bin. And so you start to grow the true value of the histogram. And the confusion noise that you get from all the other galaxies in the other panels starts to disappear. And in reality, well, maybe I'll go to the next slide so what I didn't talk about before I say that. There we go. In reality, again, not reality, it's all simulation, we don't have detections yet. But Walter Del Pozzo, a couple of years ago, decided to put Schutz's method into practice with simulated catalogs, simulated events. He wanted to see the plot from his paper, where you're seeing a typical error box on the sky of a particular event, and you can see all the galaxies that he's associated inside this error box. There's a lot more than my particular sketch, only 3 or 4. But what Walter showed, and again, I could have checked. You want to? Okay, sorry. The confusion noise, Walter claimed that after approximately 50 sources, 50 detections, that confusion noise allows you to pinpoint the Hubble parameter down to a few percent. So the width of that histogram bin is only a few percent in the Hubble. So yes, that's Walter's based on Bernard's method, and also based on the method used for Lisa by Hogan and somebody else. Okay, statistical arguments. I tend to mess this up, and I feel especially bad today because one of the authors of the next slide is in the audience. So, the idea here is, imagine you have a mass distribution of sources. in redshift 0 around us. And that represents the scatter in this plot. So what I'm applying here is redshifted mass, church mass versus redshift. As you go to higher redshifts, this population, as long as it's a constant population mass distribution, will get redshifted. So things up here, we would observe them to have higher church mass because higher redshifted church mass because they're at higher redshift. When we then detect all of these things, we will get a distribution of signal-to-noise ratios. And that signal-to-noise ratio distribution sketched over here will be a function of a bunch of things, one of which is the cosmological parameters that dictate what's happening in the local universe. And that's what this omega is supposed to represent. So the histogram, or the fit to the histogram that you may get, would be governed by cosmological parameters, but also you have to make some assumptions here about the star formation rate, and also your initial mass distribution, and specifically say the binary neutron star mass distribution. But I'm assured by Stephen Taylor, that everything is cool, and these things don't really affect you too much. And I should go on to the next plot, because this is a plot from one of Stephen's papers. And again, expanded on in 2011 based on that previous idea from the 90s, where mass distribution, star formation rate are included in the model. And here is a two-dimensional posterior distribution on the Hubble constant that you may get out of an analysis like this for advanced LIGO. And another of their parameters that they marginalized over is the mean of the neutron star distribution. So they don't assume they know that distribution. They only assume that it's a Gaussian distribution. And they claim that you can get the Hubble constant to approximately 10% with 100 sources. So again, this is another way to constrain the Hubble constant from gravitational wave measurements. Okay. I've gone a lot faster than I did before. Right, so now I can slow down and talk about things I suppose. So using tidal signatures of binary neutron star mergers. So, first of all, the neutron star equation of state. This is a sort of famous plot. People may have seen this kind of plot before, where you can plot the radius of a neutron star versus its mass, and depending on the equation of state, how a neutron star is constructed, you can have various different curves on this plot. And the key thing a couple of key things to get at the moment is that we don't know which equation of state is correct. There are some observations of neutron stars, for instance, an observation of neutron star systems like this one would say that any curve that doesn't pass through this can't be the right equation of state, because you expect the equation of state to be universal. You expect all neutron stars of a given mass to lie on one curve. There has to be one true curve. I think there are some caveats with that, but in general you expect them all to live on one of these curves. And I say here, it's not crazy to think that the neutron star equation of state will be well understood by the era of the third generation gravitational wave detectors, not least because the second generation gravitational wave detectors is going to try and constrain the equation of state through the detection of the tens, if not hundreds, of gravitational waves that we see with the advanced detectors. So, here. So tidal deformation, which is closely linked to the particular equation of state you will have for a neutron star. So each neutron star's tidal gravitational field deforms the other star. And here is just a sketch of this, where you have the dashed line is its spherical state, and the black line is it being deformed tidally by the compatible masses in orbit. A couple of things to note. The equation of state sets how a neutron star mass will respond. Different equations of state will give you different amounts of tidal deformation. And the tidal deformation not only just makes the neutron star look a different shape, actually affects the waveform that we measure in the gravitational wave detection. And in fact, it extracts energy from the system, and these neutron stars plunge a little bit faster into each other at the very end of their inspiral. And here, for anybody that's interested, is the extra phase that you may get in one particular representation of the tidal phasing change that you get in an inspiral waveform. And you can see it is a function of a bunch of things that you're familiar with: the total mass, the symmetric mass ratio, but also these lambda parameters, lambda 1 and lambda 2. These are representative of the tidal deformation parameter of each of the stars. And even though they will both, because they're both neutron stars and they both will have the same equation of state, they will have different masses and different radii and therefore have different values of these lambda.
Chris, are those lambda parameters related to each other?
They are, no, they're also, on this plot, this answers your question.
Oh.
Tell me if you here is, we're plotting lambda as a function of the mass of one of the neutron stars, or each of the neutron stars. And here are different curves for different equations of state. So pick your favorite equation of state. I like MS1, because it gives you the most tidal deformation. And pick a mass. Now, your two neutron stars may have two different masses, and therefore on this curve, they're going to have two slightly different lambda parameters. So each equation of state will provide different level of deformation, and it's a different level of gravitational wave phasing, depending on the equation of state. And as I said, I like this one, because it gives you the most effect. It's mostly measurable. But we could be in a situation where you have an equation of state down here, which would be less measurable. These particular curves here, to know the advanced LIGO and Einstein telescope, are kind of trying to indicate where we would be sensitive to specific individual sources and be able to detect this tidal signature in individual sources.
Assuming some distance.
Oh yes, they'd have to assume some distance here. I'd have to check the paper. I'm sure it's slightly too close. Right, so the tidal deformality is also a function of this thing called the love number, K2, which is related. So the lambda, this doesn't really help you, but it's a function of this thing K2, and you get a radius to the fifth power coming in as well, which is a function of the mass. The radius is a function of the mass, and also a function of the equation of state based on that first plot with the funny S's. Okay. So again, just to reiterate the effect on waveforms, what you see here, this is frequency versus noise. There's a few detected noise curves and a typical characteristic signal binary neutron star signal here. I think it's a binary neutron star and a binary black hole, actually. You don't get this tidal signature for black holes. They don't have equations of state. This is only for the binary neutron stars. And you can see where this effect comes in. They come in at these high frequencies right at the very end of the inspiral, only in the last couple of cycles of these sources. And here is a measure of...
the distance is important, right?
Yes, sorry about that. I don't think it's too... Oh, no, this is going to be quite close, as you'll see with the initial LIGO here. So this is pretty close, but the point of this is not where it comes on these curves. I was just trying to show they're coming in at this frequency. And these are the typical, so amounts of phase you're getting from these inspirals. At the very end, the contribution from the tidal phase. And the important curve here, we have the green, the red, and the solid blue are for different lambdas. The maximum lambda is blue, so you're getting most. But typically, the scale here in radians is of order a few radians, so of order a few cycles. So it's really changing, potentially, depending on the lambda, depending on the equation of state, depending on the mass, you are getting a change, an extra cycle or two, which is detectable in our waveforms. Now here is the key part about what I want to talk about with regards to cosmology. And I'll get this wrong, I'm sure people will want to ask this later. It's actually very simple, but I do mess it up all the time. With post-Newtonian waveforms, as I stressed earlier on before, the only mass term that comes in is a redshift mass. In all the equations of the waveform, it is redshift. You only ever see m times 1 plus second. M times 1 plus second. If you add this tidal signature, that breaks that degeneracy, and there suddenly appears things that have n in and not z. The amount of tidal phasing you get is a function of the intrinsic mass. It's not a function of how far away it is from. And so you get this, it breaks the degeneracy, and if you apply this to your templates, when you try and detect these things, when you try and do parameter estimation, you're now able to measure the true mass and the redshift and the distance. We could always measure the distance. So now, and I don't care about the true mass particularly, but now we have the redshift and the distance, and we can put them on the Hubble parameter plot.
But just one, you're assuming that this is
this expression was to simplify. I simplified it and had the two neutron stars being exactly the same. In the previous expression, there are two lambdas. It doesn't change things because that you're making a measurement of the equation of state rather than. It complicates the maths. I just put this in. The key thing is that you broke the degeneracy. You have something that has mass but not redshift mass. So it allows us to estimate the mass and redshift. And this is the best and most boring plot I've ever made in my career. And it was based on a Fisher matrix analysis of this particular effect. So again, not super accurate. Fisher matrix is an approximation, but all we wanted to do was see how well you can measure the redshift on these things. And it turns out we did it with three different equations of state. On this axis, we have the fractional redshift error in our measurement. And on this axis, we have the redshift. This is a third generation Einstein telescope detector. This is a third generation issue, by the way. Don't get excited. You can't do this in the next 5 years. We can see out to a redshift of a few of these sources for the Einstein telescope. And for my favorite, you can see here's my favorite equation of state. Lowest fractional error in the redshift down to sub 10% levels in redshift. But with typically other equations of state are in the tens of percent error for these redshifts. So again, imagine Hubble diagram, you've got redshift and luminosity distance, you're putting points on there, but each of those points now has a reasonably large error. But for Einstein telescope, we get millions of sources apparently. So there will be millions of points on that plot, all with quite bad errors, but millions of points. So that's quite great. There'll be far more than the supernova standard candle results, but they have better errors. So we don't quite know who's going to win. But as I said at the very beginning, the electromagnetic community is probably going to do something far better in the next 20 years anyway. But this will be completely independent. I'll do the time. So the cosmological implications of this, I just said it, is that we can measure the redshift to order 10%. We measure luminosity distances typically to order 30% for a standard compact binary inspiral. Or we may have Einstein telescope, unfortunately, because we haven't detected things, has a similar error in its rate estimate as well, extrapolating into the future. So we have potentially between 1,000 and 10 million sources, binary neutron star sources per year for the Einstein telescope, or other third generation. I'll stress again, such a thing will be independent of the cosmic distance ladder and immune from its potential systematic errors. However, we will have our own calibration errors. So one thing I talked about calibrating against the cosmic distance ladder, but we have calibrating H of t, our strain from the gravitational wave detector. That is an issue that nobody has really addressed because these are all things for in 20 years' time. But we will have to address them if they're doing cosmology with that sample. And here is a plot from one of Safia and Chris Van der Broek's papers, where this is just to exemplify in the ET regime, you have lots and lots of points that you can put on the Hubble plane. What they've done here is only looked at those that you might expect to have a gamma ray burst in coincidence with it, so they're getting their redshift errors. The errors in the x-axis are non-existent or very, very tiny. And the errors in the luminosity distance are also reduced because for gamma ray burst observations, if you see them in coincidence with a gravitational wave, you kind of expect them to be face-on to you, right? So that reduces a lot of the degeneracy in your measurement of the luminosity distance, and you can get the vertical error bars here to be quite small. But try and imagine this with big fat y error bar, x error bars, bigger y error bars, but also multiplying the number of samples on here by 1,000. And that's what you can do with this tidal. Okay. Finally, the thing I was actually going to talk about. Using the hypermassive neutron star phase of binary spirals, the bit after the binary spiral. Okay. So, the general idea here is that after the spiral, these things will merge, two neutron stars will merge and be highly unstable and form a hypermassive neutron star, something too heavy to be a neutron star on its own, sitting there quietly. But because it's such a violent process when it's merging, it can stay up as a neutron star before collapsing to a black hole for an order tens of milliseconds. And at that point, it's orbiting the orbit of the two sort of simulation from Takami, one of my collaborators, of a particular neutron star showing how this is a density plot of the thing and in the first 10 milliseconds of its motion. And one thing I should say here, that the idea is that there are particular signatures encoded in the equation of state, encoded in the frequency components we will measure in the very short waveform that we will get from this inspiral, this hypermassive neutron star. And this is again where I went a bit crazy with the animations. I'm sorry about this. So this is from one of Takami et al.'s recent papers, and it shows they've done a study with different. Each one of the colours is a different equation of state, and each one of the rows is a different mass neutron star. And you can see that there is a sort of common qualitative sort of similarity between these waveforms. And I will just zoom in. I think. Yes. Right. So they all typically have this kind of characteristic where after this is the inspiral, there is some kind of messy merger thing, and then it settles into what's known, sometimes known as bar mode instability, where it's rapidly oscillating, but it has these particular, you can see there's sort of characteristic frequency, right, that we can measure. We only have a few, we have a order tens to hundreds of cycles to observe it. So we don't have particularly good SNR or resolution, especially because the SNR is low because this is a very high frequency. This is after you're getting into the cloud sensitivity region of the detector. Here is the same but in the frequency domain. Sorry about this. What has been observed in these simulations, in these numerical simulations, is that there are these frequency components that stand out, and they happen in all of the different equations of state simulations. They happen at different frequencies, but qualitatively you get these things. You get F1, F2, and some people argue whether there's an F3 or not. But we've done some work based on F1 and F2, these typical frequency markers that you get in this bit of the waveform at the very end, just after the instant.
So this is not sort of the full waveform?
No.
This is just very...
So the dashed line is indicating where, so the inspiral would have gone off up here, but that's been cut off and also not included in the simulation because it costs a lot of compute time. So, okay, I think I'm running out of time, but what we did, we had some earlier waveforms from these guys, from Takami and Solar in Germany. And we had 5 waveforms of a single equation of state at 5 different masses. And here is a representation of them in the frequency domain in the power spectrum. Similar to the previous plot, I did this, they did the other, so it's going to look slightly different. And we modeled this as having 2 frequency components, and you can see how these evolve with mass. As you go to higher mass, frequencies go to higher frequencies. And you can kind of hand-wavingly argue that higher mass neutron stars, as I just talked to my first years, higher mass neutron stars are more compact. They get smaller as you add more mass to a neutron star. Something smaller will have a characteristically higher frequency. So what you're seeing here is the frequencies for a given equation of state for a higher mass, more compact neutron star move to higher mass. And now here, as I said, the idea that we had with the tidal thing, this is the corresponding idea with this, with the hypermassive neutron star phase. So bear with me. Okay. This is a redshift and gravitational mass plot. So just this can either be Chern mass, but let's just say the total mass of the system for simplicity. If you make a measurement of the inspiral phase of one of these objects, you are able, remember the plot with Father Ted, the comedian thing, you get this line, you get this curve where you're able to say what the redshift, you have a constant measure of Chern mass, of redshifted mass, so redshifted mass. So you're able to draw this curve in this plane of mz, because you've made a measurement of m subscript. Right? I'm also not including any of the tidal work here, by the way. When you make a measurement of one of these frequency components in the hypermassive neutron star phase, you are able to draw another line that is orthogonal to this you're able to make a separate measurement that breaks the degeneracy. And you can highlight, and this is just a sketch obviously, and you can isolate a region, which then is your posterior distribute, gives you your, a more accurate measurement on the redshift and the mass, and breaking the degeneracy again. In other words, there is a frequency marker in this signal, which you should know what the frequency is. And when you observe it as redshift, and therefore you can infer the redshift. And there is slight complications of the mass because the frequency moves with mass as well. I'm sorry that was not being very clear explanation. But maybe you'll be convinced by the results we have. So I'll just go back to this plot, the two things sweeping past each other and breaking the degeneracy. And on the final plot, these are actual results. It's a little bit messy, but if I do want to zoom in again. Here is actual results that we got from simulations, obviously not from real signals. And the green here is representative of what you might measure from the inspiral. And then you break that degeneracy with measurement of these frequency components inside the high-mass neutron star frames. And we've got two measurements because there are two frequencies that we see. And so then we get this posterior distribution, the redshift, and mass plane, this white blob, which represents our new measurements on redshift, basically in the x-axis. I've got to stress, this is all fun, I like doing this, but I'm not trying to sell it to you. This is the Einstein telescope, and it only makes this measurement of things at relatively low redshifts. These are advanced LIGO distances using a third generation detector. But again, it gives you this separate measurement you can make. And you can combine this measurement with tidal measurements as well, and really pin down more tightly what the redshift is. And then start making points on your Hubble diagram and start doing cosmology. I think that is the end of the talk. I'll just summarize. Gravitational wave source Hubble observations, they will be very useful cosmological probing to measure and detect these objects. They will provide measurements independent of the cosmic distance ladder, but they won't be as accurate as measurements from the EDA community at the time that we make these measurements, but they will be independent. We have a bunch of different methods with and without relying on electromagnetic counterparts. We will have the problem, I didn't talk about this in any detail because I don't really know. I need to talk to gravitational experimentalists about calibration being really what calibrations are going to do to us for this work. We should start comparing our potential sensitivities to future electromagnetic sensitivities. And I just want to stress that this is all very good, but the excitement right now is about first direct detection of gravitational waves. So, thank you very much.
We have time for a couple of questions. Okay, if we don't have, sorry, John.
Is that okay if I do it in a few minutes? So you showed these nice plots of how you can constrain of how you can do cosmology using the Einstein telescope, and this is particularly with the tidal deformation work.
Yeah.
And you mentioned you get error bars of, I forget exactly, but a few percent, or maybe 10%, or tens of percent.
Tens.
But then you have thousands or hundreds of thousands. You have many sources if you have something like Einstein telescope.
Yes.
So allowing that Einstein telescope someday exists. What I didn't, I mean, when I looked at the paper, what I didn't see is you never go the extra step of combining those two numbers and saying, well, so if I divide by root n or something, I get a measurement like this. And I didn't see that in your talk either. And I wonder if there's a reason why you don't like to quite give that punchline, or if you want to give that punchline now.
So I would love to give that punchline. There's a couple of sides to that. We could have done something very simple and just said a root n in the statement. I think we were page limited because we were aiming for PRL. So that's the main reason. But it's also actually proved quite difficult with collaborators to do the full problem correctly in a full, lovely, Bayesian way. And Choni and Walter Del Pozzo himself have been very, very slowly working on this for the last 2 or 3 years, on and off. And we hope to have a paper. Unfortunately, anything with ET isn't really high priority. So it's for fun, in a sense. And there will be a paper coming out saying how accurately we can make these measurements. Choni might be able to say more about that.
Yeah, so as Chris was saying, it's difficult to simulate and do the full parameter estimation on 10,000 sources, 100,000 sources, and so on. But if you, I mean, for reading, I think up to 1,000, and you start to, for different parameters, start to get into the orders of even fraction of a percent sometimes. Of course, it makes some certain assumptions that might not be very fully founded. But that's the order of magnitude that we start to get, not just on the Hubble parameter, but also on the energy density.
What's the probability that you can extract any of these parameters with a LIGO observation?
With
Say you've got one observation with a reasonable estimate.
One observation can't do it. You can't make the redshift measurement using the tidal information for advanced detectors on its own. That's right. It's gone below the noise curve at that point.
For pretty much any observation we would make with a detector that had a numeric parse.
Yes, I think the exciting thing about advanced LIGO science regarding tidal stuff is to actually constrain the equation of state. So that's what can be done, and again, that's Johnny and Walter who have said we can put all the detections of advanced LIGO gravitational wave detections, put them together and try and constrain the equation of state, which is exactly what we need in order to motivate doing this in the future, because all of this was based on knowing the equation of state. So I've jumped a step. The more interesting relevant thing for right now is the equation of state measure. But that's not my
constrain where you are in the color of your graph before, right? In your later tables, not yet before the.
hang on.
I mean, I guess you can't really say. I mean, do you have to constrain the equation of state to be able to extract meaningful information about the frequency? When you make an observation, you have this measure one of these frequency peaks in the.
Yes, you definitely need to have a particularly tight constraint on the equation of state, which we're kind of. I'm taking advantage of the fact that it's 20 years in the future. But there, we're trying to establish which one of these lines. It's not going to be any of these lines. These are just models. It's going to be something that looks like these. And hopefully, advanced LIGO detections will constrain to some fuzzy level. Ben Lackey just put out a paper last year, I think, that really looks at this very well. Of trying to constrain a fuzzy sort of region that you can say where the equation of state really lies.
One more question that's maybe a little bit similar to what John asked, but thinking that this is 5, 10, 20 years into the future, depending on long time things, you're showing that you are doing the parameter estimation by taking the first half of the signal in spiral, getting some parameters of that, getting the second half of the signal, getting some frequencies, and getting some other parameters of that second half, and then docking them together on the same dot, and then doing the process. But thinking 20 years into the future, how likely do you think it is that someone will have a model of the complete waveform and able to give you, taking as input masses, lambdas, redshift, give you the entire waveforms, including F1 and F2, and thereby bypassing the need of having to fit separately in spiral and the hyper-neutron star?
I would very much think that in that time we would do this all in one go. It's just, so this is something we couldn't do now. It's ad hoc, it's a bit messy. It was simply to show the concept that there is information in that part of the waveform. And I would expect we could do better than the results I show, but still, it's not going to be orders of magnitude better. I think that's an interesting thing, but it's not going to be a killer. This is going to make gravitational waves totally powerful. I think I put my faith in the tidal stuff more. And I should stress, I'm sorry, that final piece of work is with Sarah. I forgot to say this, I rushed. Sarah started this whole thing off in Cardiff before she came.
And you have time for one more question? Jen?
I'm curious, maybe this is a question for Johnny as well. In any of these things, so we talk about advanced LIGO and we talk about Einstein telescope. But there's a middle step that people talk about as well, which is, you know, LIGO. I think it has different names, but in other words, there's possible, you know, it's possible to squeeze another factor of 2 out of the existing advanced LIGO facilities. And I wonder if, as you do these studies, if you've played around with that, and if you see any you know, potential there.
I have not played around with that. I would very much doubt that a factor of 2 would help us cosmologically with tidal things, and definitely not with the hypermassive neutron star phase. In terms of equation of state constraining, I think that would really help factor of 2, which would then consequently help us in the future for this cosmology stuff.
Okay, let's thank all the speakers.